Hello, AP Calculus BC students. Welcome to e-learning day 6. Happy St. Patrick's Day. Aaron go brach and all that stuff. We're going to jump right in. We have a new topic today, topic 7.9, and it's a brand new aspect of exponential growth, and boy, it's extremely pertinent in terms of what's going on in the world. So we're going to be able to look at some real life data and kind of compare that to what we are actually studying here. So there really aren't, the examples are not, they're not numbered like per se by examples. There's actually, I think, a few multiple choice questions and at least one free response that we're going to look at. So this examples 1 and 2 may be a little misleading. It certainly was nice, or could be nice, if you guys could download and print that document from Schoology. If you're watching this tape delayed, I would pause this if I were you and go ahead and download it and print it. It's going to be a lot easier for you, but you should be able to follow along nonetheless. We will discuss a homework assignment and a quiz that covers topic 7.9. So we're going to go ahead and move on to, oh yeah, this, we were talking about what happens when people get socially isolated, right, or quarantined. Well, remember, this is the room right here. This is where all of it happened. This is where Isaac Newton basically discovered and invented calculus during his quarantine from Cambridge. So, hey, all I'm doing is just asking you guys to learn a little bit about logistic growth, right? So it looks pretty minuscule now. Not sure why, but I don't have this document up. That's not good, is it? So let's see if I can take care of that, you guys. So much for sitting here and getting prepared for this thing. Got it. Okay. What you are seeing here is the remnants of our AB session. Okay, this looks a lot better, right? This is the logistic growth that we're talking about. So in AB calculus, you might remember a year ago that the exponential growth model was derived from the fact that the rate of change of a variable is directly proportional to the value of that variable. And we basically drew it up as the difference, the rate of change, dy dx is equal to k times y. And this might be some things that you had forgotten, but this sort of beget that really easy form called kect. And if we try to graph things in kect form, they look good for a while. I mean, they might look something like this, but then they just grow without bound. And the problem with that is that's just not how things in the real world work. Now, at the beginning, a kect model might be very, very analogous to what's actually happening. But as time goes on, it's typically that this growth is going to be curtailed. And this could be the population of an animal that would be fighting for resources, or in the case of nowadays, perhaps it very well could be our situation with infectious diseases that we are trying to curtail. So no matter how you think about it, we have this different kind of growth model. And the upper limit, L, is kind of what we become very interested in, because in essence, this growth model is going to look a little something like this, and it has the ceiling to it. And that upper limit, L, is called the carrying capacity. And it represents the maximum population that can be sustained as time increases. So the model for logistic differential equation, you guys, is a lot more complicated. It looks a little something like this guy. I'm going to go ahead and highlight him so you can all see him a little bit better. And, a couple of things to point out here is if that population was really small, let's say that the Y value was basically, for all intents and purposes, 0, then basically 1 minus 0 kind of is meaningless, and then dy dt equals k times y. In other words, it is this exponential growth if that population is very, very small. But if that population Y approaches something close to this carrying capacity L, then we can see that we have 1 minus L over L, which means that everything gets wiped out, right? Ky would be multiplied by 0, which just is simply saying to us that there is no more rate of change. Nothing is growing anymore, right? We're done growing. The disease has been eradicated, or there are no more baby meerkats being born in this population because the population has reached its max, okay? Now, we are not going to solve this differential equation. I've shown this to students in the past. It's not real pretty. It's not a lot of fun, and I don't think you get a whole lot of benefit from it. Now, the algebra and the calculus associated with separating these variables and solving is certainly within your realm of understanding, because you'd have to use partial fraction decomposition to do that, okay? So we're going to go ahead and just look at the solution given to us for the differential equation. And then it's possible in Thursday's session, we might talk a little bit about its origin, but not so much. We're not going to have really too many more long sessions. This probably will be our longest session of the week, and then we can wrap up with 2 shorter ones and just have really a Q&A on Friday. So these are the 2 working models that you want to use, right? On the left-hand side, that is your derivative form. That is your differential equation form. And on the right-hand side is if we were to go about solving that and get y by itself and do all of the calculus and algebra that that entails, it gives us this form that sometimes I call L over 1 plus Becht. L over 1 plus Becht. And I want you to note that the k value here is technically treated as a positive. That's why I have to put the negative in front of it. Because if you have a negative exponent in a denominator, that means that that is a positive exponent in the numerator, which is what we want to have here for growth. Okay, so let's look at some of the kinds of questions that you guys would see on the AP exam that just really has you focusing on these 2 forms and answering questions based on that. So they say that a differential equation of a logistic form is given by this model. It's sometimes the case that you're given these forms. It's not always the case that you are. So I would like you to try to commit these to memory. Now, what kind of motivation do you have to do that in the short term? Probably not a lot, because even on your quiz this week, you can definitely look at your notes. But as far as the AP exam is concerned, I would love for you guys to have these, retrieved if need be. And I think you'll start to get a feel as you see these logistic questions in your mock exams about how many of them seem to give you the formula versus how many that don't. So we have the differential equation form. We're told that this is what its solution looks like. The question is, find the solution of the logistic curve model for this differential equation given here with an initial condition provided as well. All right, so we go about taking care of this. And calling up my key here, guys. Give me a second. So what we got to do is we have to sort of move from this differential equation to that form by understanding what components are there. And if you look at the original differential equation form that I have up here in the orange box, it doesn't quite jive real well with the differential form that you have here with this dy dt. And I think one of the biggest things that students will see is that we have a 10 here as our first term in the parentheses, where in our differential form in the box, we have a 1. So that is one of the first things that you want to draw your attention to. In other words, you guys will want to turn that 10 into a 1. You want to do whatever it takes. And unfortunately, subtracting 9 is not what it takes. All right. So what we're going to do is factor out a 10. So this dy dt, this thing that we have, if we factor out a 10, we would have a 2 times 10 or 20 with the y in front. And then of course we have our 1 minus, and then you just got to be a little clever. What happens when you factor a 10 out of a y? Well, wouldn't that y sort of have to become a y divided by 10? because if that 10 were distributed back through, the 10s would cancel and you remain back to your y, right? So basically, if you're factoring out a 10 from something that doesn't have a 10, you just divide that thing by 10. And hopefully this resonates with you guys, because from this picture here, you can extract a lot of meaningful pieces of information. You can see that the k value, which resides before the y, is the 20. And maybe even more importantly, you can see that the L value, the L, which is the carrying capacity, is going to be a 10. Right? So whatever population this was, it can only grow as large as 10. And I know you're thinking, well, what population grows as large as 10? Well, who knows? Maybe this is a very small, isolated space, or this could be a situation where each of these are measured in thousands, okay? The K is something that I don't want you to focus on too much and worry about. You know, basically the K is a constant that just belongs in this particular problem. The K value for the coronavirus is certainly different in Italy as it is for the United States or maybe even South Korea, a country that has seemingly have handled it very, very well. All right, so that's kind of interesting when you take a look at data from different countries and you can see the impact that the measures have with social distancing and quarantine and so forth, and how that manifests itself into this K. So if we go back to this problem, I'm going to ask you guys in the chat, which one would you go for? Which one of these 4 choices do you think most closely models this situation? Just type in an A, B, C, or D. Okay, guys doing a good job. Okay, good. You know what? I'm surprised nobody took the bait on C. Does everyone see what's wrong with choice C? It's got a little issue with it, and boy, is it a subtle issue. Good, Mackenzie. No negative sign. Hey, this is the model that we would love coronavirus to take on. That would be exponential decay, right? Because you have a very large value here in the denominator, okay? But yeah, in this case, B is the right answer. So guys, really, that's a very common kind of question on the AP exam. You don't have to do a whole lot of rigorous manipulation algebraically, but you just have to recognize the components of these equations. Okay, let's take a look at our next problem. I think it's another multiple choice. I think that we start off with several multiple choice here. Here it says the number of phytoplankton specimens in a laboratory tank at time t is increasing according to the logistic growth model. These little guys are just competing, finding food and space and so forth. So it says, which of the following statements could be true? Okay. I'm sorry, was there a question I may have missed, Mackenzie?
Yeah, Ethan typed a question in the chat, and it's a really good question.
Oh, sorry, man. See, I get so carried away that I missed stuff. If not,
good.
every answer had a 9 for B. So let's go back up to this. If not every answer choice had a 9 for B. Oh, thank you. And this is something that's going to happen later on. So I knew that this was coming. That's sort of why I neglected this. But Ethan's exactly right. The fact that every one of the answer choices had a 9, or at least I should say -9, right, for B, the way that you would find that specific B value is to use that initial condition. So in other words, if I took what we felt to be our expression, right, we felt pretty confident that the L was 10, and we have 1 plus Becht, right, where we felt that the K was going to be -20, but we're not so sure what the B is. We would, of course, plug in 1 for Y, and by the time we plug in 0 for T, let's see what happens. We plug in 0 for T, and that wipes out the whole e to the 0, right? Or the e to the 0, I should say, becomes 1. So 1 is equal to 10 over 1 plus b. And when we cross multiply, you can see very shortly that your b is going to be 9. Okay, I guess I dismissed it because, you know, this answer, well, you know what, let's talk about that. No, because D, I should have mentioned this because D was so incredibly close that we certainly needed to solve for B. Okay, I was so hung up on C's variation. So really, in order to answer this, you guys needed to do the 0, 1. And that's an excellent job, you guys in the chat, getting B so quickly. Maybe you guys are like working ahead of me. Maybe I'm going too slow, right? I'm just going too slow. All right. So we'll have to remember that in the future to check for those B's. Okay. Now in question 2, the phytoplankton problem, which of the following statements could be true? We'll just kind of go through these systematically and just kind of see if we can maybe point out some things that may not make sense. And I'll tell you what, you guys, it's very difficult to answer some of these questions that I'm about to ask in the chat, but I am never going to make anybody unmute themselves if they don't feel comfortable with this, okay? I would love for people to unmute and even give wrong answers because that would spawn a really good discussion. Because guys, trust me, I've taught long enough. If somebody in my math class gives me a wrong answer, there's at least 3 or 4 or 5 more people just within 20 feet of that person that are probably thinking the same thing. So is A good answer or not? Is A good answer or not? And the answer is a not, right? The answer is a not. And the reason is because, I think you guys kind of mentioned this earlier. If nobody chimes in, I'll just go ahead and talk about this. The answer is because the exponent of that E is positive, right? And that's what really leads us to saying that this problem is decay, okay? Charlie asked about the B value, like, does that lead to a shrinkage? And in this particular case, if I go back to this previous example, it's kind of confusing because the B and the K sort of have this symbiotic relationship to an extent. And the way that they interact with each other can kind of work in tandem to tell if we're going to decay or grow, okay? And if the K were some certain value that might be positive and the B some negative value, well, would that potentially cause for this denominator to get smaller and smaller and thus for this to still grow, right? Even if this negative K took on a positive value. So there is some truth in what you said about the B having a little bit of an impact of whether we grow or we shrink, okay? In this particular case, since we have a B value in front of this E that's positive 1, this guy's going to end up shrinking, or I'm sorry, yeah, shrinking or decaying. So that's bad. All right, B, anything about B that's bad? Well, B can't be correct because, well, this is not even a logistic differential equation, right? This is what we call a normal differential equation, a normal curve, right? Something growing by 3.5% with each passing time element. So it just doesn't have the elements that a differential equation should have. That's logistic. What about C, guys? What's the first thing that you can say? You can probably type this in the chat. If the second derivative is positive, what does that say? What does that say about a curve? The second derivative being positive means that the curve is concave up. Good job, you guys. Logistic growth curves, guys, what do you think? Are they always going to be concave up? Answer is no, right? Glancing down at the next example, I think illustrates that pretty well. That's a pretty good looking logistic growth curve, right? That's the whole idea of reaching this carrying capacity, that we have to change from concave up to concave down. So this statement can't be true for all time. Okay, it's going to be true for some of the time. So that really only leaves D to be the correct answer. So of course we can somewhat confidently circle it in, but I'd like to talk about why. And basically the reason is that it's adhering to the differential equations I guess, form. Now, it looks as if there was a moment in time when maybe this guy was not separated. In other words, it's possible that prior to this, that dt had been located in the denominator of the left, and maybe this p 1780 minus p might have been multiplied over there to the right. And then this 0.35 is just probably some constant that's part of the K perhaps. And if you look at this really closely, this adheres to our formula to an extent. Now maybe we'd have to factor out the 1780 to get this to be a 1. But this had the makings of the logistic differential equation. It's just that it was in the process of being separated and then being integrated. And I like this problem because it kind of shows you what we would be looking at if we had to integrate this. Hopefully you can see the partial fraction decomp element there, and we would split this apart into two fractions, right? A over P plus B over 1780 minus P. But you know, the AP exam will never, ever ask you to solve a logistic differential equation. So, okay, hopefully that makes sense to everybody. We're going to move on to the next question. This is another fairly quick question that doesn't require a lot of work. It says, the spread of an infectious disease to workers on a large floor of an office building is modeled by this logistic equation. Wow, kind of appropriate, right? I had this problem written years ago. T is the number of days. P of T represents the number of infected people. The graph of P of T is shown. What is the number of infected people when the rate at which the disease is spreading the greatest? All right, so we have to read this very carefully. Let's point out some issues first. That 800, do you all see how that's the carrying capacity? All right, it's very likely that the carrying capacity of this office is 800 because there happens to be 800 people that work there, right? If there are 800 people in an office, doesn't matter how bad this infectious disease is, 801 people are not going to get sick. So that's how a carrying capacity can sometimes work in its worst possible incarnation, right? Where everybody gets affected. The question here, though, was what is the number of infected people? So that sounds like that's one of these values along the y-axis, right? It's not denoted, but I could certainly write this in for you. This would be our people, and this would be our time. I guess these were days, okay? So what is the number of infected people when the rate at which the disease is spreading the greatest? So we have to figure out, guys, where along this graph does it look like the rate is spreading the greatest? The rate is spreading the greatest. The rate is a maximum. The rate is a maximum. Well, that's not talking about the maximum of the graph, right? It's talking about the maximum of the derivative of this graph, right? Good job, Prob. So what we're going to do in this problem is we have to think about along this curve, where is that place where the derivative has its largest or steepest value? And I'm going to go ahead and jot it in for you guys. It's going to be right here. It's right there. And yep, the answer is 400. So we've pretty much got the question answered, but I want to give you guys a little bit more insight, because if you come away with this problem with just two really basic, simple ideas, you will never miss one of these questions. Anybody tell me what that point is? It's definitely half the carrying capacity, like Pravir noticed. That is exactly right. But if you think about some of the concepts that we talked about last year in AB, the feature of that graph, nice job, Noah, right? Noah may not be the only one who's thinking it. Maybe some of you are typing it, but great job, Noah. That is the point of inflection. So if you have a curve and you have information about the point of inflection, the point of inflection is always going to be the place where the derivative is changing the fastest, because after this point, the slopes are actually starting to get gradually smaller, all right? And that point of inflection always occurs at half the carrying capacity. And you see, that's what we have to know. You guys, you nor I can really tell that that blue dot's the point of inflection from this graph. but we have enough information from the graph, from the stem, to see that, oh, L right up here, the carrying capacity was 800, so therefore half of that's our answer. Okay, so hopefully that makes sense. Okay, good job on this, guys. Multiple choice question number 4. The rate at which gas is being extracted from an underground reserve at time t satisfies this diffie-q. So we have dg/dt equal 0.04 g times 1 minus g over 64. So hey, I think we have a legitimate differential equation that's logistic in our normal form, right? If you guys look back at the first page of the notes, that's exactly what we were wanting. G is measured in thousands of cubic feet, T is measured in weeks. For what value of G is the extraction rate increasing the fastest? So for what value of G is the extraction rate increasing the fastest? So I don't want anybody to type this in. I want everybody to get a chance to think about it. All right? Everybody think about it. And I want to do something a little different on this one. Because it's so easy to get influenced by what other people's might have said before you, do you mind giving me privately a private chat message, A, B, C, or D? Right? I love this interactivity, guys. Good job. I know for those of you watching this tape delayed, you don't really quite get this benefit, or teachers out there that are watching this, but right now what's going on in the chat with Zoom is that the kids are able to throw in their answers. So this is good. And it's really good because it's anonymous. They're not going to be called out for incorrect answers, but I can kind of see where the understanding lies. And we have lots of different answers, guys. We have 3 of the 4 choices that have been selected. So it's definitely worth discussing. All right. Looks like most everybody, I'm not going to count them up, but it looks like most everybody has been able to come up with something. So let's take a look at what we've got here. Again, I'm going to tell you what I'm going to do. I'm going to back up just for a moment. I'm going to take this guy. I'm going to do a little cut and paste. That way I don't have to scroll back and forth. So where's my clipping tool? Where's my snipping tool? Right there. So I'm going to tell you what, I'm just going to snip all of this. Let's give this a good snip. Snip. And then let's go minimize you. And whoop, too far. Too far. And let's go ahead and paste this. It's very sluggish when I'm running the software with Zoom in the background. All right, so what we've got here on the upper left is our logistic differential form. And if you really look at this piece by piece, all of the components are there, right? And if we look at it even closer, we see that the L is located underneath the dependent variable, right? As long as you have 1 minus out in front, right? So we can certainly say that in this problem, L is 64, which is the carrying capacity, okay? Now remember what happens when we reach our point that we increase the fastest. That occurs at half of that carrying capacity. So you just cut that 64 in half. So you see how it's just really a matter of being able to find that L value. And of course, know that you're going to cut it in half. And it's kind of remarkable how that question is very similar to this question, right? It's just that they're 2 different kinds of modals, right? You've got a graphical approach here, right, in multiple choice question 3, where you've got more of an analytical approach here in multiple choice question 4. Okay, and even though your homework, you guys, is not very long, I think it's a 6-problem homework, and that's really what you're going to be doing for the rest of the week. I really tried to give a wide array of modalities, but without having you do the same thing in a exhaustive, repetitive way. All right, so it's one of those homeworks that if you really spend some good quality time with it, it takes care of all the issues that you have to overcome. Okay, and then it's like, wow, I kind of showed you my hand, so I don't really have too many other things up my sleeve that I could put on a test. So the quiz is probably going to contain similar kinds of things. All right. We've got a comment here. In calculus, the carrying capacity is seen as L, which makes it makes a lot more sense because in bio you call it K. Oh no! Oh my gosh! Yeah, in calc we call K that constant of proportionality. So that's unfortunate. So yeah, that's going to be something that you'll have to battle a little bit. So yeah, and then yeah, Mackenzie, I believe that's what's going to happen. I think Thursday. I hope by then that's going to have given you guys enough time that you could do some good Q&A over this, and that's pretty much what I've got planned. And I think Friday, I think I'd like to do some Q&A, just a short little Zoom Q&A. We could solve a few CML questions together. So that's really got the plan for the week going into spring break. Let's go ahead and take a look at this FRQ if you guys don't mind, and this will wrap up the notes part of this. And then I got some really neat data to show you. I think you guys are going to really love some of this coronavirus data that fits into differential equations, and let you guys think about what countries are showing logistic growth already and what countries are showing just crazy out of control exponential growth. So we have a conservation organization that releases 30 panthers into a preserve. After 3 years, there are 30 panthers, and then the preserve has a carrying capacity of 150. The growth rate of the panther population is given by a differential equation. So see, here is a situation where I didn't really burden the kids with having to memorize these. I gave both forms. So first job, find L. L shouldn't be too crazy, right? L should be pretty much there in front of us. We just have to recognize that L is the carrying capacity. So we just know that 150 is our L. So don't think AP Bio with K, think L. Okay, good. Now we take a look at B, and Ethan had really kind of alerted us to this. So with B here, what we do know is that if that L was 150, then we have the semblance of a logistic growth equation that looks like this. The number of panthers can be modeled by that at any time t. Now I know it seems a little scary, like, well, how are we going to be able to go in here and find B when we don't know K? But it turns out that if you're given an initial condition, right, a condition when time is 0, that K doesn't really matter a whole lot, does it? And so that's what we want to recognize here, is that the ordered pair 0, 30 can be used, right? And when I say 0, 30, I mean the 0 to be the T and the 30 to be the P, right? Population, panther. So if we solve this out, 30 would equal 150 over 1 plus b times e to the 0 once again. So that makes that denominator just 1 plus b. And if we cross multiply, 30 quantity 1 plus b equals 150. It's really up to you if you want to distribute the 30 through. Sometimes I think it's just as easy if we don't, especially if that 30 is a divisor of the 150 or a factor, and it is. We get 5, I believe, and then we subtract the 1 over, and boom, before you know it, we've got our B value, okay? Taking a look at C, it says now, hey, find the exact value of K, and let's not write it as a decimal. So in order to find the exact value of K, there's got to be some more information that has been provided, and that information is in the form of, after 3 years, we have studied that there are 30 panthers. So it's just the ordered pair 3, 50. And it's probably likely that you guys might remember this a little bit from last year when we were solving our differential equations that weren't necessarily logistic, but we had to do things like this in order to find that constant of proportionality. So if you recall, we have this population equation that would be P equal or 50 equal, and then the L is still 150 over 1 plus, and remember the B is 4, right, that we just found, and then E would be raised to the negative K times 3. I'll just put that negative 3 in front of the K because it looks a little bit better. Okay, and now we get, I don't want to say the arduous task, that's not a good word for it, but we get the wonderful task of getting to solve this for the K. All right, yay for us, right? So if we go ahead and cross multiply, 50 times the quantity 1 plus 4e to the negative 3k would be equivalent to 150. And notice how I was a little cautious there. I didn't want to necessarily distribute the 50, especially seeing that it nicely divides over to the other side. So we get a 3 there, right? And then we can go ahead and subtract 1, which gives us a 2, and now we're on our way, right? Now we have this in a form that in just a few more steps, we should be able to solve it for k. But it's probably likely that a little recap of this is in order. So if we divide by 4, that gives us 1/2 on the right side. And about the only way that you can solve this is to take the natural log of both sides. So I'll just write that out in long form. It's likely that when you guys do these, you might be able to do this step in your head. And then the next step is what you would write, and that's when the good old exponent of the e, remember how that can come in front? And just to highlight this, I'll rewrite the ln of e afterwards, but the ln of e we all know is going to be equal to 1 anyway, so he's going to drop out. So then when we solve for this k, the k is actually going to be negative 1/3 times the natural log of 1/2, right? Now, I know that we discussed about how the value of this k, right? We always thought that k was going to be positive if, in fact, that there was a negative already in front to demonstrate growth. And it seems like we have a k that's negative right now, and then 2 negatives will make a positive, and that seems to indicate decay. But do you guys ever think about what the sign of natural log of 1/2 is? Anybody know if it's positive or negative, perhaps? The natural log of a half? Yeah. It's negative, you guys. It is. And a lot of times, and this might seem kind of cheesy, and I don't want you to feel like this is you're obligated to do this. This k would work, but it's also legal for you to let that negative exponent or let that negative reside as an exponent of 1/2. And so therefore, this would be equivalent to positive 1/3 times the natural log of 2, right? You know, if we call up the good old TI Inspira here, there's a nice little graph that I'm working on for AB, everybody. But if we call this up, and I think I can get rid of all of this safely. So if I type in negative fraction 1/2, and then multiply that by the natural log of 1/2, or I think I had a 1/3 in front, if I'm not mistaken. So let me change that to match this problem. All right, and I'll put a decimal in there to get decimal output. But if I did the same thing, but with now positive 1/3 times the natural log of just 2, notice it is the same result. It is the positive k that we were anticipating, and that positive k has a negative in front of it, so that's going to reside in the denominator, of course, and then be our growth. Okay. Part D, you've already done the dirty work, so this is awesome. It says write a model for this panther population. So like I said, you've pretty much have done the worst part of this. So you could just say, okay, let's put the panther in some pretty clothes, right? P of T, and that would be equivalent to 150. There's a site, panther in some pretty clothes. A panther in a tuxedo, I like it. I like it. 1 plus, right? And then our B value is 4, so that's probably kind of giving us even more indication that we'd put a plus there. E to the, and then I think it goes negative k, so negative 1/3 natural log of 2 times your t. Okay. And this is a very powerful model for us because with this model, if you are interested in figuring out what is the panther population at time 5, we could plug 5 in for t. Let's say we're interested in something else. Let's say, oh my gosh, in time 10, right? What in our units in time are measured in days or years, I'm sorry, years. So let's say in 10 years, we want to revisit this preserve, and we want to know how many panthers should we expect there to be? Well, we could let the TB10, right? Or let's say that we want to know when are there going to be 100 panthers, right? So we'd plug 100 in for this, and we could figure out what the time is going to be. Okay, so there's lots of different things that you can do with this. Oh, and I think that's what we are doing, right? In part E.
Mr. Record,
Yes, ma'am.
for part D, if
Mm-hmm.
we wanted to do the ln of 1/2, is there a way we can do that? Because I just know in my mind I would not have figured out that ln of 1/2 was negative.
Yeah, if let's say that your part D looked like this. You know, you had the K already negative, right? That double negative would cancel each other out. And I guess you're looking at this, right? As your exponent of the E, and that is
Yeah, I just wasn't
perfectly
sure if we
allowed.
could.
Yeah, the only thing that I worry about that, Mackenzie, is whether or not that would match multiple choice. But you know what? Here's the thing. If this was a multiple choice question, then the problem that you said that you might be faced with probably won't be an issue, because then it'll be on your radar to see those manifestations because of the multiple choice answers. But in free response, I would completely take a problem like this one, right? Even though it, you know, it would take somebody of some certain mathematical know-how, which includes all of you and hopefully most days me, to see that this is a negative value, right? Because of the natural log of a half being innately negative. But good point. Okay. Part E, use the model to estimate the panther population at time 12. So this is just what I mentioned. We're just going to plug a 12 in for the T, and no doubt this is going to require a little TI Inspire intervention. So I'll bring this in, and I don't really think that there's any need for us to define this P of T, because we're only going to use it, I think, really one time. So I'm going to do that. Try to do this in such a way that I can see both things simultaneously. So I think that'll work. I think I asked you guys this the other day. You can still see both my calculator screen and my notes. Is that right? Anybody in the chat say you can see both the calculator and the notes? Okay, so I'll take 150 on top over 1 plus 4. Okay, we are going to multiply that by E, and that E is raised to a fraction. I could really use either one. Will I mess you guys up if I use Mackenzie's? All right, I'll just do that. And then I have another fraction here. Whoops, I meant to say fraction. There we go. And I might want to put a decimal in here so I can get some decimal output. So there's my E raised to the K value, right? Where I've already taken care of that negative. And if I multiply this by 12, this should spit out some panthers, right? Okay, good. Yeah, they do overlap. That's kind of what I wanted, just to be able to see both of these. So we have 120 panthers in this population. So P of 12 is 120. I don't really know what you guys could write for any more work than this. That would be acceptable. And then F, you know, it looks like, oh my gosh, this is so complicated, right? I mean, are you telling me that our job is to take the limit as T approaches infinity and have to do so with one of these two models, right? Whichever one you want to think of. I'll choose that original model where we have that negative in front with the natural log of T. Well, honestly, how many of you know the answer to this without even having to solve the limit, right? Anybody? You don't even have to do this privately. What is the answer to part F of this problem? Yeah, it's the whole point, right? The whole point of this is seeing that you guys understand that the carrying capacity is just the limit as time goes on to infinity. Now, if a student didn't recognize that, you could still answer this without the use of a calculator. It's just that you've got to be super clever and know that, okay, as this t gets super big, I'm going to multiply it by something that's negative. So I'm going to essentially get 150 over 1 plus 4 e to the negative infinity, which, you know, doesn't make a whole lot of sense, but it'll work for us. And then this 4 times e to the negative infinity acts like 4 over e to the positive infinity. And then doesn't that zero out on us, basically? So we have 150 over 1 plus 0. So there's your 150. But it's certainly acceptable just to recognize this as the carrying capacity. So, okay. So that's really it for the work that we had to do today with the problems. I think I've got a slide here. I'm going to show you some data. And the problem is the data that's coming in is changing all the time. And this is something that was extracted yesterday. And this was a friend of mine who's kind of doing the same thing. I think he's going to be reviewing logistic growth with his students, and he kind of thought that this was kind of neat. I am grotesquely colorblind, so it's really hard to kind of, for me to alienate or isolate these colors, but it is my understanding, and if I write this up, this top graph is China, right? And you see the cases here in up to 30,000, and the time factor, this time factor, I believe, is weeks. All right, now that's something that I'm sorry, no, the time factor is days. This is the first few cases, the first few instances of the outbreak. Okay, and the red graph is Italy, right? The red graph is Italy. Now, what do you notice about China and Italy in terms of logistic differential equations? They don't quite look like they've done that, right? So that's a little bit of a problem. Now, if you look at Iran in the green, obviously they don't quite have the number of cases of either China or Italy, but they still seem to be not demonstrating that logistic growth model. Now, if you look at this blue one at the bottom, this one is South Korea. Now, when it says Korea, that means South Korea, because honestly, do we even know what the heck is happening in North Korea? I mean, we'll never know. I mean, they're not going to release information to us. We're lucky we're getting data from China, and the data that we get from China is probably a little bit suspect. But anyhow, South Korea seems that it has logistic differential equation properties, right? It seems like perhaps it reached some kind of a carrying or a inflection point somewhere around there. And you look at South Korea, and what's different with South Korea as opposed to some of the other situations. Well, they took a lot of preventative measures. I mean, they were the first country to have the drive-up testing kits available. They really exercised social isolation very, very quickly. So a lot of good things happening there. Now, the United States, if you can see, it's really bad. I'm going to see if I can maybe highlight it in the same color but make it thicker. But it's this very light blue, almost Carolina blue. So it looks like this, and notice how it stops there, because they're calling this, at the time of this data, like day 8 of the pandemic. And you can see that, well, we're certainly not on the trajectory to be considered logistic. And we're growing, but we're growing still exponentially. But how so? I mean, exponential growth is a dangerous thing, because it's very scary if I sit here and tell you the United States has experienced what, a doubling of the number of people infected just within the past 36 hours. And I think that there's truth to that. I think at the end of Sunday night, it was like 2,500 or something, and now it's well into the 4,000s. Well, that's what exponential growth does. 4,000, when you look at 300 and some odd million, is a pretty small number, but it is very interesting. The graph, are these proportional, or looks at the number of cases? I'm pretty sure that this is the number of cases, but I've got something better here I'm going to show you, and it's very likely that maybe you guys have also looked at this data. It's from a website. Anybody go to worldmeters.info? It's really an interesting little website. And it basically keeps a very up-to-date, now it has ads, the ads are appropriate, I double-checked, but it has what we seem to be all of the reported coronavirus cases in the world. So we're at just under 200,000 with the nearly 8,000 deaths. This recovered is kind of interesting. What does recovered mean? I mean, I guess they're not symptomatic anymore. These are people who aren't displaying the symptoms. Maybe this is Tom Hanks, right, and his wife. That's possible. But when you scroll down a little bit farther, we see the total cases, which doesn't quite look like we can construe this as being exponential, or I'm sorry, being logarithmic. It's got this very weird little hiccup here. Now, this is scary. When you look right along here, I mean, you can't grow much faster than that, right? That's like almost a vertical line straight up. But I have a feeling that's about a time when a lot of the countries were starting to be alerted in what's happening in China. And so they took whatever testing capabilities that they had and administered them immediately. And I think it gave us a little spike in the data, right? And it kind of looked, oh, well, maybe, just maybe we are kind of, we're kind of bottoming out here. Maybe this is logistic. And then all of a sudden, the end of the first week of March hit, and obviously that's when I think Italy's cases went through the roof, and of course the United States kind of got in on the deal. So if you look at both that and the total deaths, and a linear scale, you guys, just means that the y-axis is just in even increments. It's not real encouraging, right? I don't think it's anything I should have anybody be afraid of. But and then here's the data that we can look at just with the numbers themselves, and then I can click on a country. So I can click on China, and we can look at China's cases and deaths, and we can look at China's graph. And it's interesting because, and Prabir, you already kind of beat me to the punch. It looks like, yay, China, we've reached the ceiling, we've reached the carrying capacity, but it seems like China has stopped testing, right? So I don't think that this is very factual data, even though this might look like it's good news, right? This might look like it's,
Mr. Record,
yes, sir, go ahead.
they didn't stop testing. So like if you look at something like the flu here, if you have the symptoms of a flu, they say you have the flu, essentially. So
Mm-hmm.
they do the same thing with the coronavirus because it was taking too long to get testing reports back. So basically, they just started assuming you have the coronavirus because it's more likely that you have the coronavirus in China compared to something like the flu or the common cold.
Right, but when they talk about these cases in China, the fact that I can't help but think that this number is so underinflated, because these are
I agree.
confirmed cases, but it's also coming from a state-run media country too. And I think this is the graph that I would rely on the least, right? But we can look at some other countries. So if we go, I think I can just go back here. Takes me back to that graph or the chart, and let's look at Italy. Italy will be very interesting. Italy's been a little bit more forthcoming in their in their in their information, and mainly it's because they want help. I mean, they're not going to hide things. I mean, they are open to any help at all, and Italy is certainly exponential growth. And you'll notice that this is right up until yesterday. I imagine this thing gets updated maybe at midnight or overnight, so we can have data on what happens today. So it's certainly the case that Italy, if this is truly factual information, that they are still in that upswing. South Korea is a good one to look at. Now, South Korea has a little bit lower death rate for theirs. And okay, well, South Korea, this looks a little bit like China, right? Maybe we could rely on this a little bit more. But again, as Prabir said, it's impossible to test every single living soul in your country. I mean, we just don't have that capabilities yet. So we have to kind of take this with a grain of salt. Although this might look logistically differential, is it truly behaving that way if we could consider every single person in the country? But at least we can say that the number of cases being reported are on the decline from a country that I would be more apt to trust, right? I'm sure you want to look at us, right? Why not? Let's look at the United States right here. So there's our current cases. See, we're over the 4,000. This has changed just since last night. We're up about about 1,300 or so since last night. And that's what our graph looks like, folks. So it's certainly in its worst stage of growth. right? The United States has got to be the country that we want to trust the most on the data. But again, the logistics of being able to test everyone is sort of going to make this, tough to comprehend. But the fact is, the number of people who are being tested and are coming in positive is still growing. And I think we should expect it to do this for a little while, and then we start to see what kind of benefits our social isolation has. So, but it's interesting. If you guys ever are curious about this, just worldmeters.info and then /coronavirus. I haven't checked some of the other information on this. It's just a neat little website that, when you don't get to watch a whole lot of sports on TV, this is kind of what you gravitate to, right? So, all right, guys, anything else for the good of the cause? Any other questions that you all have? I got a feeling that this time next year, I'll have a really good logistic differential equation to share with my BC students, right? Over the data that is yet to be acquired. And I'm very optimistic there will be a next year, guys. You're going to go to college. You're going to have just an unbelievable memory to share with your kids about this when you get older. So hopefully everybody knows where to find stuff on Schoology. So just to make sure, this is Power School. I don't want Power School. Let's go into Schoology, guys. And in Schoology, if you go to either one of your periods, period 2, for instance, will work. I kind of did a little reorganization so that you could find things a little bit better. So in the e-learning homework assignment folder, if you click him, you should see this topic 7.9, interpreting the meaning of logistic growth in context. And eventually, you guys, you give me a couple of days, but I will have a sort of an interface through Schoology by which you can input some of these answers. And I may do the same thing with 7.5. I think I just might combine these into one single assignment. And to be honest, you guys, I typically grade those by completion. If you enter them into Schoology, I do look that you have at least half of them right. And because if a kid just like gets 20% on it, it's likely that they just kind of clicked random things and maybe didn't put a lot of effort in it. So you should score a 10 on this if you have a majority of them right. And then we'll put the quiz up later on Friday for you guys to input. And you can almost imagine that the quiz is going to have to be multiple choice. It's too difficult sometimes for you guys to input mathematics into Schoology. So that is the plan. And then if you have a whole bunch of extra free time, right? Because it's not like we're going to watch a play-in game for the NCAA tournament tonight. You could turn your attention, like I said yesterday, the Continental Math League. I do have our 2 and only 2 practice exams that you can start looking at, but the due dates for those will not be until after spring break. Okay, remember, the only thing that I want you guys to do during spring break is to work on that mock exam. And if you don't have the mock exam, whether you're here in the chat or watching later, at this point, I want you to reach out to me, and we could arrange a drop-off at that point, because I'd like to get as many of these in your hands as possible, because it just will make the time a little bit easier when we get back. After we get back, it's possible that I might just have to set up a meeting time like I did for the IUPOI, where you have to come and pick it up. But again, I have to get permission from people in order to do that. So, all right, I think we're going to go ahead and call it here. Got us right at an hour, it looks like. So, okay, great job. You guys I'm really proud of you. I've bragged on you to a lot of people, and I'm really proud of what you guys have been able to accomplish. So just keep it up. I'm going to stop the recording. I'm going to say a few other things to you guys.